All right, hello and welcome to my EngPhys 2A04 Lab 5 presentation. My name is Luke Wilson. All right, so to start off, we'll just go over the agenda for this presentation. So first, I'll give a brief explanation of the theory behind my final design. I'll give a demonstration of the device by showing a video clip of it working. And then finally, I'll give an explanation of this device, why I chose this design over others, and what I took into consideration while implementing parts of my design. Okay, so to start off, we just have some important theory to go over to kind of get a basic understanding of how my final design ended up working. So the first main concept that we'll be focusing on is magnetic force. So a current carrying conductor in the presence of a magnetic field experiences a magnetic force that is given by this equation. So it says that the magnetic force is equal to the current flowing through the conductor times the length of the conductor crossed with the magnetic field that it is located within, or that is acting on the current carrying conductor. Okay, so that's the first little bit of theory that we're going to cover. Okay, so the second thing that we're going to cover is because in this project I built a motor which entailed coiling up a long piece of wire, suspending it on its axis, running a current through it, and holding up a magnet for the magnetic field lines of the coil and the magnet to interfere and produce a force which rotated the motor. We're going to look at how current flowing through a coil produces a magnetic field. So as we can see from this illustration in the middle, there is a current carrying loop, and when a current flows through a conductor, there is a magnetic field that is induced that flows around that conductor. So in this case, since the current is flowing kind of in the counterclockwise direction here, we have the magnetic field lines going up and to the right on this top part, and down to the left on this bottom part, and kind of through in this center part. So this is the magnetic flux that's induced by this current, and the magnetic field due to this flux is given by this equation. So this equation states that the magnetic field due to a coil of wire is equal to the number of turns in the coil times the permeability of free space times the current flowing through the wire over 2 times the radius of the coil. Now the last little bit of theory that we'll touch on before we move into the design is magnetic torque. Now magnetic torque is given by this equation. So it's the field that is acting on the coil, or whatever magnetic dipole you might consider. In this case, we're considering a coil, so it's the magnetic field acting on it, times the current flowing through the coil, times the number of turns of the coil, times the area of the coil, which is given by pi r squared. All of this times the sine of the angle of the magnetic field that is acting on the coil. So down here, there's just a visual depiction, just kind of a review of torque. So we have a wheel kind of on its axis, and there's a force acting upon it on this end, pulling it down, and the torque is equal to the distance times the force, and it is in this case, the z hat direction. So yeah, we are going to move on to a visual demonstration of my final working device. Okay, so as you can see, it's not really moving until I hold the magnet up close to it, and then that's when the field lines start to interfere, the magnetic forces act upon each other, and it causes the coil to spin around its axis. So here are some images of my final design. So as we can see in this middle image, basically what's going on here, so let me just explain how this works. This is the positive terminal of the voltage source. Current is flowing through from the positive end up into these little paper clips that I fashioned to be kind of supports, so it's easier to see in here. But yeah, basically I stuck the paper clips into the breadboard up and over, and then made a little closed loop here at the end so that the ends of the wire could be fixated within these supports. And then once I had that set up, I just took an entire loop of wire and made a coil of wire with 32 turns, or 34 turns rather. And then, supported the coil by wrapping the ends around. I sanded off the ends of the coil so that it would be conductive, or the ends of the wires, which are inside these little holes with the axis on which the coil is rotating. And then, I use this voltage source over here to supply voltage to the circuit, to flow a current through, which induced a magnetic field within the coil and allowed it to rotate. So just going back to kind of, as we wrap up this presentation, so as we can see, there is, let me just play this video. So it's not really moving, and then all of a sudden, this is producing a magnetic field that's going this way. There are magnetic flux lines kind of flowing through here. And as this gets closer, these magnetic field lines interact with these magnetic field lines, and it produces a force which causes it to rotate around its axis. And I chose this design just because it was the simplest and the simplest demonstration of the basic theory behind this concept. And just to reflect on this lab, I got more familiar with using the lab equipment, got used to trial and error because this required a lot of debugging, and it also helped me visualize magnetic field interactions. Thank you for watching.